Hello and welcome to Lecture 10, Energy. In this lecture, we're going to talk about kinetic energy, gravitational potential energy, spring potential energy. And then we're going to use those different types of energy and the law of conservation of energy to solve some problems. So energy is defined as an object's ability to do work or to move an object with a force. There's different types of energy which we're going to look at in this course. The first type is called kinetic energy, and the symbol for kinetic energy is going to be E with a subscript of K. Okay, so this is kinetic energy here. Kinetic energy of an object is the energy that it has because it's moving. If an object is moving, then it has to have kinetic energy. If it's not moving, it doesn't have any kinetic energy. The formula for kinetic energy is EK equals 1/2 mv squared. That formula will be given to you on any test and exam. 1/2 times m, which is mass, times the velocity, which is the object's speed in meters per second. You don't have to include a direction there, squared. Notice that there's no vector on top of EK, and that's because it's not a vector quantity. There's no direction associated with energies at all. Okay, so energy is a scalar quantity. So that makes things a little bit easier because you don't need to worry about adding vectors by decomposing them and adding them together and recomposing them. These are just numbers that you can add to each other as you would any other numbers. Okay, so it's a little bit easier to work with. So if you want to add energy terms, you can just simply add the values. You don't need to decompose any vectors. All right, so let's practice a problem together. Very simple one. The question says, find the kinetic energy of a 9-kilogram baby who is crawling at 0.40 meters per second. So we're simply just using the formula for kinetic energy, EK equals 1/2 mass velocity squared. And we're just going to sub in all the values that we know. 1/2 the mass of the baby. It's already in SI units, so we can just leave it. The speed of the baby, again in SI units, so we don't need to convert anything, squared. A lot of people forget the squared, so just be very mindful that you haven't forgotten it. The formula is given to you, so you shouldn't be forgetting it. So I'm just going to type this in, 1/2 times 9 times 0.4 squared. And I get 0.72. Now the SI unit for energy, no matter which type of energy, is the joule. So as long as your units that you put in for mass and for velocity were in SI units, then for energy you're going to have joules. So that's why you want to make sure if the units were not given to you as SI units, you need to convert them first before you sub them into the equation. All right, let's move on to gravitational potential energy. All right, so the symbol for gravitational potential energy is UG. G for gravitational, and U is what the letter is that they use for potential energy. So all the other types of energy we're going to discuss are potential energies, so they'll have U's there instead of E's. Okay, so an object that has a height above the surface of the Earth possesses gravitational potential energy. Even though the object's not moving, it has the potential to move. It can fall downwards and gain kinetic energy. So for example, if I'm standing on top of a bridge, let's say, and I'm going to bungee jump, if I were to step off of that bridge, I would have the potential to move really fast. But when I'm at the top of the bridge right at the very beginning, I'm not moving. I just have the potential to move. So I have gravitational potential. The reason why I'm able to move when I step off the bridge is because I have a height. The formula for gravitational potential energy is UG equals mgh. Again, m is the mass in kilograms. G is acceleration due to gravity, so it's the 9.80 meters per second squared. And then h is the height of the object. Now, every time we deal with gravitational potential energy, we need to define a reference position. Okay, so it's mentioned here. H is the height above an arbitrary reference position. So every time you use this formula, you need to just decide where you want the reference position to be. And this will make a little bit more sense when we start to do more complex problems, okay? So let's try question 2. It says, if the ground is defined as 0 height, so that is the reference position, is the ground. That's where the height is 0. What is the gravitational potential energy of a 60-kilogram lady who's about to bungee jump off the edge of a 35-meter tall bridge? Okay, so I'm just going to put in the formula for gravitational potential energy, UG equals mgh, and I'm just going to substitute in the values that I know. The mass of the lady is 60 kilograms. It's already in SI units, so I don't need to convert. G is 9.80 meters per second squared. And the height is 35 meters. She's on top of the 35-meter tall bridge, and the ground is defined as 0, so she has a height of 35 meters relative to the ground. So 35 meters. All right, and now I just have to plug this into my calculator. 60 times 9.8 times 35, and I get 20,580. Again, this is units of energy, which is the joule. All right, and that's it. Moving on to the third type of energy we're going to discuss in this course, which is elastic potential energy. All right, so the symbol for elastic potential energy is UE. E for elastic, U for potential energy. Okay, so elastic potential energy. It's often referred to as spring potential energy as well. So some people will put a little S there instead of the E for spring potential, but we're using an E, and that's how you're going to see it on your formula sheet. It's referring to the energy that's stored in a spring when it's either stretched or compressed. So if you have a spring that's just sitting there, nobody stretched it or compressed it, it doesn't have any energy. But if you were to stretch it, it has the ability to move an object. So right now, if you stretch it and you hold it stretched, it's not moving and it's not able to move anything because you're holding it. So it doesn't have kinetic energy, but it does have elastic potential energy, because if you were to just let go of it, it would cause something to fly or move. Okay, so a spring that is stretched or compressed is not moving. It still has the potential to move if you let go of the spring. So the formula for elastic potential energy is UE equals 1/2 K delta X squared, where K is the spring constant, and that kind of tells you how stiff the spring is. The units for spring constant is newtons per meter, so you need to make sure everything's in SI units when it's given to you. If not, you would have to convert it. And delta X represents the amount that the spring has been either stretched or compressed from its equilibrium or its rest position. So let's say a spring is regularly 3 centimeters long, and you stretch it so now it's 7 centimeters long. Well, now it's been stretched 4 centimeters, so 4 centimeters would be that delta X. Again, you would have to convert centimeters into meters, and then you would have your delta X value in the correct SI unit. Okay, so let's try out question 3. With question 3, it tells us that the elastic energy stored in your tendons can contribute up to 35% of your energy needs when you're running. So your tendons is where a lot of the energy is stored when you're running. Sports scientists have found that your knee extensor tendons in sprinters stretch 41 millimeters, while for non-athletes, they only stretch 31 millimeters. The spring constant of the tendon is 33 newtons per millimeter for both groups. So how much energy are sprinters and how much energy are non-athletes able to store in their tendons? So this is really two separate questions. We're looking for the elastic potential energy in a sprinter's tendons and the elastic potential energy in a non-athlete's tendons. So let's just divide this up into the two parts. I'm going to write sprinters and non-athletes. And let's write down what we know about the two. Okay. So for a sprinter, we know that they can stretch their knee extender tendons 41 millimeters. So that's how much it's being stretched by compared to the regular equilibrium or rest position of their tendon. We're treating their tendons like they're springs. So the delta X for the sprinter is 41 millimeters. And it says for a non-athlete, the delta X, the amount that they can stretch their tendons, or the spring that we are modeling this with, the delta X is only 31 millimeters. The spring constant, which is K, is the same for both groups. It's 33 newtons per millimeter. How much energy can the sprinters and the non-athletes store in their tendons? So we're looking for UE for the sprinter and we're looking for UE for the non-athlete. All right, so before we can start substituting in values, we need to make sure that every value that was given to us is in SI units. Otherwise, the unit for energy will not be in joules. And so then we'll have to figure out what those units are. It's a lot easier if we just put everything in as SI units. Okay, so let's do that on the side. All right, so delta X for the sprinter is 41 millimeters. Let's convert that. So I'm going to just do this on the side here. 41 millimeters. We want to change that over to the correct SI unit for distance, which would be meters. So I'm going to cancel out millimeters by putting it in the denominator and put meters in the numerator instead. 1 meter is equal to 1,000 millimeters. And when I multiply those with each other, I get 41 divided by 1,000, which is 0.041 meters. Okay, so that's what my delta X is for the sprinter. Now my K value. I have 33 newtons per millimeter. I don't want newtons per millimeter, I want newtons per meter. So I'm going to get rid of millimeters by putting it in the numerator, replace it with meters in the denominator, and 1,000 millimeters is 1 meter. So I'm multiplying 33 times 1,000, which is 33,000 newtons per meter. Okay, so I'm going to do the same thing for the non-athletes. I have 31 millimeters converted over to meters. So I have 0.031 meters, and then my K value is still 33,000. Newtons per meter. Okay, because it's the same as the value for the sprinters. Okay, so now that we have that information as SI units, I can go ahead and plug my values in for both cases. So I have UE for the sprinter is equal to 1/2. My K value is 33,000. My delta X is 0.041 squared. And now I can just type this on my calculator. 1/2 times 33,000 times 0.041 squared. And I get 27.74. And my unit for any type of energy is the joule. Now we can go ahead and do the same thing for the non-athlete. Elastic potential energy of the non-athlete equals 1/2 K. My K is still 33,000. Delta X, which was 0.031 squared. I'm going to just type this on my calculator. 1/2 times 33,000 times 0.031 squared. And I get 15.86 joules. All right, so you can see that the sprinters are able to hold more energy in their attendance compared to non-athletes. So this takes us to the law of conservation of energy, which states that energy cannot be created or destroyed, but it can be converted from one form to another. That means that energy is conserved. So the total amount of energy in a closed system is always constant. So we can think of it as the total amount of energy initially is equal to the total amount of energy final. Now we can split up the types of energy based on the ones that we're using in this course. So we have the sum of the kinetic energy, gravitational potential energy, and elastic potential energy initially has to equal the sum of the kinetic energy, gravitational potential energy, and elastic potential energy final. Okay, so the total energy that we have initially has to equal the total amount of energy we have final. So let's use that information to work on question 4. We have a 30-kilogram boy sliding down a slide which is at a 30-degree angle to the horizontal. If he starts at rest from the top of a slide, which is 3 meters above the ground, first, how fast will he be traveling when he gets to the bottom? Okay, let's start with just a little diagram here. We have a slide. Here's a boy at the top of the slide. It's at a 30-degree angle to the horizontal. He starts from rest at the top of the slide. So initially he's at the top of the slide and he's not moving. So his speed is 0 meters per second. The slide is 3 meters above the ground. All right, so we're going to figure out what our initial velocity is, our initial height is, our initial delta x is. And then we're going to do the same thing for final and solve for the unknowns. Okay, so initial is when he's at the top of the slide, final is when he's at the bottom of the slide. Now, before we can begin, we need to think about what our reference height is. Okay, so when we talk about gravitational potential energy, it equals mgh. That h depends on where we decide to put our reference height. Now, most of the time, people will choose the bottom of the diagram to be the reference height. So that means like right here, I'm saying my height is 0. So that means up here, what is the height? Well, the slide is 3 meters above the ground, so this height over here would be 3 meters. And it's as simple as that. You can decide anything to be your reference height. You could have said the top over here, my height was 0, but then that would mean that the height over here would be -3. Right? So you could do that as well, and that's totally fine, but it confuses a lot of people. So I usually say that the bottom is where my reference position is. So that's what I'm going to do here. Okay. So now that we know where our reference position is, I'm going to state all the values that I know. We already said the V initial is 0 meters per second. Then that means that the height initial, the height when he's at his initial position, which is at the top of the slide, is 3 meters. What about at the end? The V final, that's what we're looking for. The question says, how fast will he be traveling when he gets to the bottom? So this is my question mark. And my H final is 0 because he's at the bottom. We also have delta x's. Delta x initial, delta x final. Delta x is how much a spring has been stretched or compressed. But in this question, there is no spring at all. So it hasn't been stretched or compressed at all. So it's just 0. So I'm going to put it in there just so that you can see that it's there, but it's 0. There is no elastic potential energy initially or finally in this question because there's no spring involved at all in the question. Now that we know all of our variables initially and final, I'm going to use the formula that we've highlighted above to solve for the unknown value, which is V final. Okay, so we have E total initial equals E total final. I'm going to put in all the different types of energy that we've discussed in this course. Kinetic energy initial, gravitational potential energy initial, and elastic potential energy initial is equal to those same types of energy final. Now I'm going to sub in the equations for each of these. Okay, so the formulas will be given to you on a formula sheet for all your tests and for your exam. So the formula for EK is 1/2 mv squared. Since this is the initial, I'm going to put a little I for V initial. For UG, the formula is UG equals mgh. This is the initial, so I'm going to put an I for initial height. And the formula for elastic potential energy is 1/2 k delta x squared. And again, I'll put a little initial for my delta x since it's the initial position or the initial stretch or compression of the spring. I'll do the same thing for final. My kinetic energy equation is EK equals 1/2 mv squared. This is the final velocity, plus for my UG, it's mgh with the final height. And for my elastic potential energy, it's 1/2 k delta x final squared. So now I can just sub in all the values that I know. If I want to, I can also, instead of subbing in right away, I can rearrange for the one that I'm looking for. Well, what is it that I'm looking for? It's V final over here. That's the variable I'm solving for. So I could take all my other variables and move them to the other side and then get rid of the 1/2 m by dividing it out and then square root both sides with a plus or minus. Or I can sub in everything right now. I'm going to go ahead and just sub everything in right now. So I have 1/2 my mass. So my mass of the object is 30 kilograms. V initial is 0 squared plus my mass is 30. G is 9.80. H initial is 3 meters plus 1/2. My K, I don't know what it is. I'm just going to write K. My delta X initial is 0 squared is equal to 1/2 mass is 30. V final is what I'm looking for plus M, which is 30. G is 9.8. H final is 0 plus 1/2. I still don't know my K, but there is no spring, so my compression or stretch is still 0. Okay, I'm going to go through and just cancel out everything that has a 0 in it because anything times 0 is just 0. All right, so I'm doing this to show you that you can plug in all the values you know into the formulas and certain ones will cancel away and become 0. If I go back to the original equation or the second line here, that means that EK initial is 0, 1/2 k 0 squared, that became 0, that was my UE initial. My UG final is 0, and this is 0 as well. I can save a lot of time by canceling them out right away rather than moving on to this fourth step over here where I plug in my numbers. All I have to do for EK is if I know the velocity is 0, then the EK is 0. For UG, if I know the height is 0, then I know the UG is 0. And for UE, if I know that there is no stretch or compression in a spring, and in this case there's no spring at all, then UE is 0, so I could just cancel it right out without having to sub in any numbers. Makes life a little bit easier. So now I'm left with this line here that says 30 times 9.80 times 3 equals 1/2 times 30 times V final squared. And now all I have to do is really just solve for the V final. Okay? So I'm going to do that. So I'm going to divide both sides. Actually, let me just simplify this first. So I have 30 times 9.8 times 3, which is 882, is equal to 1/2 times 30, which is 15, times V final squared. Now I'll divide both sides by V final. Sorry, I'll divide both sides by 15. And I get V final squared is equal to 882 divided by 15, and then I'll square root both sides. With a plus or minus. And I get V final is equal to, I'm just going to type this on my calculator, the square root of 882 divided by 15, which is 7.668 or 7.67 meters per second. It's asking me how fast will he be moving. So we're not looking for a direction. We're just asked for speed, which is a scalar value. No direction is needed, so I don't need to worry about the plus or the minus. I'll just give the positive answer. That's how fast he's moving. All right. So that was part A. Now in part B, the only difference is that instead of the boy who was 30 kilograms going down the slide, we have a 60 kilogram mother that goes down the same slide. Again, starting at rest, we want to know how fast she's going to be traveling when she gets to the bottom. Okay, so the process is all exactly the same. We get to this step right here, and the only difference is that the 30 would become a 60 instead. So let's just go ahead and change those 30s into 60s. So I'm going to write 60 times 9.8 times 3 is equal to 1/2 times 60 times V final squared. Okay, everything that got canceled, I'm just not writing it at all. So how is that going to change my answer? Should we go ahead and type it all up and see? So we have 60 times 9.8 times 3, and that's 1,764 is equal to 1/2 times 60, which is 30, V final squared. Again, I'll divide both sides by the 30. So now I have 1,764 divided by 30 equals V final squared. I'll square root both sides, and I'll end up with V final is equal to plus or minus the square root of 1764 over 30. And now I can type this onto my calculator. 1764 divided by 30, all in a square root sign, is 7.67 meters per second. Well, it's the same answer that we got for part A. Well, why is that? How is it the same answer? Let's do a little bit of work on the side to look at this a little closer. So if we take a look at this step right here, where we have 1/2 mv initial squared plus mg h initial plus 1/2 k delta x squared equals 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. Okay, so that's our original equation really. It's all the energies with the equation subbed into them. If there's no elastic potential energy in the question at all, because there's no spring involved in the question at all, we can take that out, right? So I can rewrite this equation and it looks like this. 1/2 mv initial squared plus mg h initial equals 1/2 mv final squared plus mg h final. Do you notice a value that's in both sides of the equation in every single term? there's an M, a mass, everywhere. So we have mass, 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 and mass 4 times. What we could do is factor out that mass, 1/2 V initial squared plus GH initial equals mass, factored out again, 1/2 V final squared plus GH final. Since we're able to factor it out, we can then divide both sides by mass, and they cancel out. So really, what you could do is anytime you have an equation that has the same variable in every single term, they could all just get canceled out. And that means that the speed of the boy, when he gets down to the bottom of the slide, does not depend on his mass. It doesn't matter what mass you plug in there, you'll still get the same answer. So whether it's the boy, who's 30 kilograms, or his 60 kilogram mother, who slides down the slide, they'll both end up at the bottom at the same speed. Okay, so that's something to keep in mind when you have masses in all the terms, okay, because we didn't have those terms that had 1/2 k delta x squared in this problem because there was no spring involved. So now all of our terms have mass, then we could just cancel out all the masses and not even have to substitute values in. Sometimes you'll find that the mass is not even given to you in a question, and that's because you technically don't even need it. You could just cancel out the masses and not even plug in a value for it. Okay, so if you find that you get a question that doesn't have mass in it, don't worry about it. It just means mass will cancel out, so you won't need that value. All right, okay, so let's move on to question 5. A 1,500 kilogram car traveling at 10 meters per second suddenly runs out of gas while approaching the valley as shown below. The alert driver immediately puts the car in neutral so that it will roll. What's the car's speed going to be as it coasts into the gas station on the other side of the valley? All right, so before we begin, what we need to always do for all these questions is to define our reference height. So we can choose wherever we want to be the reference height. Normally people will choose the bottom of the diagram, so that would be right here. So this is where my height is 0. Okay, so then that means over here my height is 10, and over here my height is 15 meters. All right, so that's a really important first step. Now we can go ahead and write down what are all the initial values and what are all the final values. So initially, we know the initial height is 10 meters because this is the initial position of the car. This is the final position of the car. Initially, the velocity, it tells you the car was initially traveling at 10 meters per second. So the initial velocity is 10 meters per second. In this question, there is no delta x because there's no spring involved at all. So I'm just going to write delta x initially equals 0 meters. Okay, let's move on to the final position. Our final height is up here at 15 meters. Our final velocity is what the question is looking for. What will be the car's speed as it coasts into the gas station? So we're looking for that value there. And the delta x final, again, there's no spring in the question, so it's still 0. Okay? So when we do E total initial equals E total final, we can enter all the different types of energy that we've discussed in this course. I'll put them in the correct order, though it doesn't matter. And now before we start subbing in values, what would be nice is if we just took a look at everything, all the values that we know over here, and anything that has a 0 associated with it would just cancel that term out completely. So delta x initial is 0, so that means UE initial, which equals 1/2 k delta x squared. Anything times 0 is 0, so that would just go away. And likewise, UE final would also be 0 because the delta x final is 0. And that just simplifies our question a little bit, so we don't have to worry about subbing in that equation. Okay, so now let's put in the equations for all the values, all the types of energy that we have left. So EK initial is 1/2 mv squared. I'm going to put an initial there. UG initial is mgh initial. EK final, 1/2 mv final squared. UG final, mgh final. What is it that we're trying to solve for? The car's speed as it coasts into the gas station, V final. So V final here, that's what we're solving for. Let's rearrange the equation. We notice at this point there's a mass in every single term. Only then can we cancel all the masses out. So if you like, you could cancel them out. Then we wouldn't have to sub in that 1500 kilogram value in for mass. And if we didn't know the mass, then it wouldn't be a problem because we don't need to sub in a mass at all. Okay, so now let's rearrange and solve for the V final here. So I'm going to bring this GHF to the other side of the equal sign. So I'm going to put a minus, so that's this term over here is going to the other side. Minus GHF is equal to 1/2 V final squared. A lot of people don't like seeing halves everywhere, so what you could do is you can multiply the whole equation by 2, timesing this by 2. You don't have to do this if you don't want to, but by multiplying by 2, we're getting rid of all these halves. So 1/2 times 2 is just 1 V initial squared, and then I'm going to multiply GHI times 2, so I have 2 GHI. GHF is being multiplied by 2, so I have 2 GHF equals, and the half is getting multiplied by 2, so I have V final squared. So it just makes the equation a little bit simpler. Now I just need to get rid of that squared, so I'm going to square root both sides. So now I have V final is equal to plus or minus the square root of V initial squared plus 2GHI minus 2GH, and then this should say a final here. Final. All right, so it's a little bit easier to do it like this because you're not messing around with plugging in numbers on your calculator until the very end. So I'm going to sub in my numbers now. V initial was 10 squared plus 2, G is 9.8. H initial was 10 minus 2, G is 9.8. And H final is 15. Everything was in SI units. I didn't have to convert anything. So now I'm going to type this into my calculator. Square root of 10 squared plus 2 times 9.8 times 10 minus 2 times 9.8 times 15. And I get 1.414 meters per second. Notice the question asks for speed, which is not a vector, so I don't need to give a direction. So I don't need to put in any plus or minus. Those don't make any difference because I'm only looking for the magnitude, the value itself without any direction. So the final speed when the car coasts into the gas station is 1.414 meters per second. And that's it. Okay. All right, let's do another question here. We have a 5 kilogram box sliding down a 5 meter high frictionless hill starting from rest across a 2 meter wide horizontal surface, and then it hits a horizontal spring with a spring constant of 500 newtons per meter. The other end of the spring is anchored against a wall. How far is the spring compressed? Okay. So this question looks pretty complicated. Let's draw a picture just to make it look a little bit easier for us. So we have a frictionless hill. So there's a hill over here, and it's 5 meters high. It starts from rest, so this is the initial velocity. And then it goes across, so it goes down the hill, then it goes across a 2-meter wide horizontal surface. So this is 2 meters. And then it hits a spring that has a spring constant. So here's this spring over here, and it's anchored to a wall. Okay, so this box, which started off at the very top, over here, it goes down the ramp, then across this horizontal surface. It bangs into this spring and it compresses it a little bit, making the spring a little bit squished. Okay, so it gets compressed. How far is the spring compressed? So let's write down everything that we know about the initial state and the final state of this box or of this system. So initially, V initial for the box is it's not moving because it says that it started from rest. So its initial velocity is 0 meters per second. We have to define a reference height. So let's say the bottom of this diagram over here is where our height is 0. So that means that the height when it's at its initial position at the top of the ramp or the hill, H initial is 5 meters. And then what about the delta x initially? So there is a spring in this question. Delta x is asking how much is this spring compressed or stretched. That's what delta x means. So initially, when the box is at the top of the hill, how much is that spring that's at the bottom stretched or compressed? Well, it's not stretched or compressed at all because the box hasn't hit it yet. The box is still at the top of the hill. So initially, the delta x is 0. Okay, so let's move on to final when the box is over here and it's compressed the spring. So V final, H final, and delta x final. Well, delta x final is what we're looking for. The question is asking how far is the spring compressed? So that's our question mark. That's what we're looking for. H final is the final height of that box. So we define the reference height at the bottom of that diagram. So the height there is 0 meters. And then what about V final? How fast is that box moving when it compresses the spring to its maximum compression? At the moment that the spring gets compressed all the way as much as it can possibly be compressed, the box has stopped moving. Because if it was still moving, then the spring would still be getting compressed. So at the spring's maximum compression, the box has come to a stop for one small moment, and then the box will fly out again in the opposite direction. But for that moment when the spring has reached its maximum compression, the velocity of the box is 0 meters per second. Okay, so now we know all the initial and the final values. I'm going to write out the formula. E total initial equals E total final. I'll put in all the types of energy that we've discussed. And now let's think about which of these values can we just cancel out. So our V initial is 0. That means EK initial is 0. Because it equals 1/2 mv, which is 0, squared. So that whole thing is 0. What else is 0? Our delta x initial is 0. So then that means that our UE, which is equal to 1/2 k, delta x, which is 0 squared, all of that's going to be 0 too. V final is 0, so that also implies that EK final is 0. I'm just going to cross it off. And our H final is 0. So that implies since UG final is MGH, if H is 0, that's all going to be 0 as well. So our formula has gotten a lot simpler. Now let's plug in the actual formulas for each of these energies. UG is mgh initial. And at the end we have UE final, which is 1/2 k delta x squared final. All right, so we're solving for which value? the delta x final. That's what we're looking for. So why don't we go ahead and rearrange the formula right now. We're going to get rid of this half by timesing both sides by 2. We could divide by a half as well, and that's the exact same thing. So I'm going to times both sides by 2. So I get 2 mg h initial equals, when I times a half by 2, it becomes just 1. So I get k delta x final squared. Now I'm going to divide both sides by that k value. And then I'm going to take the plus or minus square root. So I have delta x squared is equal to 2 mg h initial over k. Now I'm going to square root both sides to get rid of the squared. And I have delta x is equal to the square root of 2 mg h initial over k with a plus and a minus in front. Okay, so the question wants to know how far is the spring compressed. Let's plug in all of our values. Plus or minus the square root of 2. The mass was 5 kilograms. G is 9.8. H initial was 5 meters. Over K, which is the spring constant, and it tells us in the question the spring constant is 500 newtons per meter. Now I'm just going to type that onto my calculator. Square root of 2 times 5 times 9.8 times 5 divided by 500, and I get 0.99. And the units for that would be in meters. Now the question's asking how far is it compressed. There's a plus or minus in front of here. The plus is if the spring got stretched, the minus is if the spring got compressed. But the question's asking how far is it getting compressed, so we can just say it got compressed 0.99 meters, and we wouldn't have to put in a negative in front. Okay, so that's it. The final answer is that the spring got compressed 0.99 meters. Notice for this question, we were not able to cancel out the masses because there were no mass in all the terms. So because we have that spring elastic potential energy, the 1/2 k delta x squared on the right side of the equation, there's no mass to cancel out there. So we weren't able to cancel out mass, which means that mass had to have been given to us in the question. All right, we have one more question here. It's question 7. So let me just fix that. And it's the most challenging type of question because what it is it combines both collisions, which is what we did in the previous lecture, and transfer of energy, which is what we're doing in this lecture. So it's a problem that involves both a collision and a transfer of energy. So it's likely that you're going to see a question like this. You have to be very careful when you see a collision happening and then a transfer of energy, because it means that you have to divide the problem up into 2 parts, a collision part and a transfer of energy part. Okay, so let's take a look at this question so you can understand a little bit about what that means. So we have an 8-gram bullet shot with a speed of 1,067 meters per second into a 4-kilogram block, which is initially at rest on a frictionless horizontal surface. Okay, so that's the collision. The bullet collides with the block. Then the bullet remains lodged in the block. So what kind of collision is that when the objects collide and then they stick together? It would be an inelastic collision. Okay, so now we have the bullet and the block together are moving into a spring. The spring has a spring constant, and the bullet block compresses the spring. How much is the spring going to be compressed? Okay, so this is a 2-part question. The first part we're dealing with just the bullet and the block colliding into each other, and we want to find out how fast are they going to go after the collision. Once we know how fast they're going, we can move on to part 2, which is the energy part, where we can say the total energy of that bullet block system, which is moving, is equal to the energy after it's impacted that spring and compressed it. Okay, so let's start with part 1. And this is that the bullet collides into the block. So it's a collision. And anytime you have a collision problem, you can always use conservation of momentum. Formula for momentum, P is equal to mass times velocity. Okay, so let's go ahead with part 1. So we have the total momentum initially, meaning before the bullet collides with the block, equals the total momentum final, which means after the two collide. So this is what it looks like. Initially, you have a bullet and you have a block. This is initial. And then final, the bullet has collided into the block. So here's the bullet inside the block. Okay? So initially, we have two different objects. We have a bullet and a block. So the total momentum of the two objects would be the mass of the bullet, I'm going to just call it BUL, times the velocity of the bullet initially, plus the mass of the block times the velocity of the block initially. Just change that. Okay, so that's the total momentum initially over here. When we go into the final, there's really only one object because this is an inelastic collision. The two objects are stuck together. So now we really just have the mass of that one object, which is the bullet and the block stuck together. So the mass of them would be mass of the bullet plus mass of the block. That's the mass of the object at the end, times the velocity of both the bullet and the block. Okay, so this is what it is that we're looking for. This is our final velocity. We need to find this final velocity for part 1 before we can move on to part 2. So let's rearrange the formula. We're going to solve for velocity of the bullet and the block together. They're stuck together. Final, which is equal to the mass of the bullet times the velocity of the bullet initially plus the mass of the block times the velocity of the block initially divided by the mass of the bullet and the block together combined. There's a lot of subscripts here. You might find them very confusing. You might want to change them. If you want, you can say bullet. You can use maybe just a little b, and block. Since it's a larger object, you can call it capital B. And that might make things a little bit easier. So you can go ahead and change the subscripts if this is getting too confusing. Okay, so before we start to plug in values, let's make sure we know everything and that they're in the correct SI units. So we have a bullet. The mass of the bullet is 8 grams. Okay, so this is the mass of the bullet, but it's not in SI units. We need to convert it to kilograms. So we have 8 grams. We want to get rid of grams, change it to kilograms. 1 kilogram is 1,000 grams. So we end up with 0.008 kilograms. So that's the mass of the bullet. And the mass of the block is 4 kilograms. Okay, the initial velocity of the bullet is given to us as 1,067 meters per second. The initial velocity of the block, it tells us it was initially at rest, so it's 0 meters per second. Okay, so now we can go ahead and sub in all the values that we know. The velocity of the bullet and the block after the collision is equal to the mass of the bullet, which is 0.008, times the velocity of the bullet initially, which is 1,067 meters per second, plus the mass of the block, which is 4 kilograms, times the velocity of the block, which is 0 meters per second, divided by the mass of the bullet, 0.008, plus the mass of the block, 4. And now we can calculate this. 0.008 times 1067 plus 4 times 0 divided by 0.008 plus 4, and I get 2.12974 meters per second. Notice I have a lot of digits here. Just because this isn't my final answer, I'm going to use this value in part 2 of the question. Okay, so now we know how fast the bullet and the block are moving together before they compress that spring. So I'm going to move on to part 2, and part 2 is there's a transfer of energy. The bullet block together are moving at the speed of 2.12974 meters per second. The spring is not compressed initially, and then the bullet and block collide into that spring and compress it. Okay, so this is an energy transfer problem. So I'm going to say the bullet block. So this one system, one object, it's the bullet and block together. They're compressing the spring. So this is a transfer of energy. Anytime there's a spring involved, it's always going to be a transfer of energy problem. All right, so now we can say energy total initial equals energy total final. Okay, so what types of energy do we have in this question? The spring and the bullet and the block together are moving with a velocity of 2.12974 meters per second. So initially, their velocity before they compress the spring, I'm going to write it here. V initial is 2.12974 meters per second. Okay, the height. We're going to say the reference height is the position that they're in initially and final. So there is no height at all. So we're saying the height is equal to 0, both initially and final, because there's no change in height in the question. So I'm going to say initial height is 0 meters, final height is 0 meters, okay? Nothing moved up or down a hill. What about the delta x? Delta x initially the bullet block has not compressed the spring yet, so the spring has no stretch or compression, so the delta x is 0 meters. All right, then we can find the final velocity and final delta x as well. So the final velocity, well, we're looking to find out what is the maximum compression of the spring. The spring will be compressed to its max when the bullet block comes to a stop for a moment. So the final velocity is 0. And the delta x final is what we're looking for. How much will the spring be compressed? That's our question mark. So now that we know what all the values are, we can put in the formula. So I'm going to put in all the different types of energy first. I have EK initial, UG initial, and UE initial equaling EK final plus UG final plus UE final. Now I'm just going to cancel out the ones that I know are 0 to make my life a little bit easier. HI is 0, so then that means that UG initial has to be 0. So I'm going to cancel that one out. Delta XI is 0, so that means that UE initial is 0. So I'm going to cancel that one out. V final is 0, so that means EK final is 0. And H final is 0, so that means U gravitational potential energy is 0. So I'm going to cancel that one out. All right, so everything that has a 0 associated with it, that energy type can just be canceled out to make it a lot easier for you, so you don't have to sub in values of 0 into all the formulas. Now let's write out the formulas. EK initial, the formula for kinetic energy is 1/2 mv. It's an initial, so I'm going to put initial squared equals UG final. Oh, I think I must have crossed off the wrong one. It was UG, that is 0, so I should cross off UG. So I'm left with UE final, elastic potential energy, 1/2 K delta X squared. What is it that I'm looking for in this question? It's the delta X. Okay. So let's rearrange and solve for delta X. Why don't we start by first getting rid of that 1/2? So I'm going to multiply both sides by 2, which is nice because it's going to get rid of the 1/2 on both sides. So 1/2 mv squared times 2 is just mv initial squared. And on the right side, 1/2 k delta x squared times 2 is just k delta x squared. Now I'm going to divide both sides by k. And then I'm going to plus or minus square root. So I have delta x squared equals, because these k's cancel, equals mv initial squared over k. Delta x equals the plus or minus square root of mv initial squared over k. Now I can plug in my values. So my mass, it was the mass of the bullet and block together. So that's 0.008 plus 4. So together it's 0.008 plus 4. V initial was that 2.12974. Squared divided by K, which is the spring constant of the spring, which should be given in the question. It's 2,400 newtons per meter. So I'm going to type this into my calculator. I have the square root of 0. And I have to put in a bracket here, so I'm going to write bracket 0.008 plus 4, close the bracket, times 2.12974 squared divided by 2,400. Everything's in the square root sign, and I get 0.087 meters. There's a plus or minus, but the question is asking how much is the spring compressed? So the spring will be compressed 0.087 meters. Or if I wanted to, I can change it to centimeters. It would be 8.7 centimeters. All right, so I hope that helps. I know this is a really challenging problem because there are two parts to it. Essentially, there's two questions in one here. You need to recognize that for questions like this, there's both a collision involved and a transfer of energy, so you have to divide the problem up into two parts. Okay, so make sure that you're able to do questions like this. Redo this question on your own and make sure you're okay with it before your test. All right, thanks so much for watching, and I'll see you next time. Bye.